Alright, so this is the lesson video for section 16.1 for honors chemistry. So we're going to go ahead and start chapter 16. It's going to be on solutions. Don't forget, an easy way to have access to all the videos is just subscribe. So let's go ahead and get started. So, properties of solutions. Solutions are homogeneous mixtures that can be solids, liquids, or gases. So, like an example of a solid solution would be sterling silver. That's a mixture of metals, but it looks the same throughout. A liquid solution, those are the ones you'll be most familiar with. For example, Windex. Again, it looks the same throughout, but it's made of some solids dissolved in liquids. And gases can be homogeneous mixtures too, like the air we breathe is a mixture of different gases. So remember, the solvent dissolves the solute. We talked about that before already. So the solvent is the dissolving medium, the solute are the dissolved particles. Now, three factors that determine the rate at which a solute dissolves are stirring, which sometimes they'll call it agitation or, shaking up a flask, things like that, temperature, and the particle size of the solute. Because what we're trying to do is get those interactions between the solvent and the solute, because if it's water with an ionic compound in it, we talked about that, we want those water molecules to be able to surround those ions. And if it's not an ionic compound, surround those molecules. It just all depends on what we're dissolving. So let's talk about each of these. So stirring a solution speeds up the rate of dissolving because it disperses the solute and brings the solute in contact with all of the solvent particles. So a lot of times when I ask how does stirring or agitation speed up dissolving, a lot of you want to tell me that you speed up the particles. Well, the particles are moving way faster than you can possibly ever stir. If you're the fastest stirrer in the entire world, you cannot stir anywhere close to how fast the particles are already moving, even if the substance is pretty cold. So you're not speeding anything up when you're stirring, you're just dispersing it. So like when we dump a solid into water, this example is marble chips and acid, so we'll just use that. The marble chips are going to settle at the bottom, so that means all of this acid up here is not in contact with the marble chips, so it can't help dissolve it. However, once we stir it up and disperse those marble chips throughout the acid can attack all the marble chips at the same time. So that's what we're trying to do, is bring the solvent into contact with the solute. So next thing is temperature. Now this is the one where we are increasing the speed. So increasing the temperature of a solution usually increases the rate at which a solid solute dissolves because the particles are moving faster. So notice this part, solid solute, because we're going to talk about gases in just a few minutes. Okay, so remember, when things are cold, particles are moving slowly, less kinetic energy. As you heat them up, the particles start moving faster and more kinetic energy. The sooner the particles can come in contact with each other, the faster it can dissolve. So last thing that we're going to discuss is particle size, sometimes called surface area. So just be aware, you might see either. So dissolving occurs only at the surface of the particle. So for example, if this is salt in water and we have our positive and negatives, it can't be salt in this picture because the ions are the same size. Just saying. But just pretending that it is. And these are the water molecules. Notice they're only touching the particles at the surface. They aren't trying to dissolve anything below the surface because they can't reach to it. Another example is this right here. Okay, the red atoms can only touch the surface. They can't reach any of this interior. And so if you can crush it up, so see here we've crushed up this big green thing. If you crush it up, there's more surface area. So see, now the red particles can come into contact with many more of the green particles. Okay, so you want large surface area or small particle size. Sometimes we'll say things like if you crush it up, like crushing up a pill to help it dissolve in a liquid so you can drink it if it's too big to swallow on its own. All right, so that's how particle size does. So next thing is solubility. Okay, we briefly discussed this earlier when we learned how to know whether something will dissolve in something else, and we learned polar can dissolve polar or ionic, and nonpolar can only dissolve nonpolar. However, now we're going to talk about how much can we dissolve. Because you've all made sweet tea before when it's cold and you try to dump that sugar in there and not a lot of it dissolves. So let's talk about solubility. So solubility is the amount of solute that dissolves in a given quantity of solvent at a specific temperature. Temperature is going to be very important. Solubility is often expressed in grams of solute per 100 grams of solvent. So it may say something like, I can normally dissolve 20 grams of sugar in 100 grams of water at 25 degrees Celsius. Now I just made those numbers up. Okay, so don't quote me on that, but I'm just giving you an example of what it might look like. The stronger the attractions between the solute and solvent molecules, the greater the solubility. So that's where we talked about in the previous chapter. If something's nonpolar and something's polar, those are not going to attract well. So they're not going to have strong attractions, and solubility will probably be 0. All right. So let's talk about the difference in unsaturated, saturated, and supersaturated. So an unsaturated solution contains less than the maximum amount of solute at a given temperature. So if this is our solution right now, and we add some more solute, it will also dissolve, making the solution more concentrated. So as long as it's unsaturated, you can still dissolve a little bit more. Now notice it's at a given temperature. Every slide almost in this PowerPoint, I seem to have to put temperature in there because all of this stuff changes with temperature. Okay, so that's unsaturated. Saturated, on the other hand, contains the maximum amount of solute. So if this is our solution, we add some more, notice it does not dissolve. It's just going to sink to the bottom. So this is when you're trying to add that sugar to that cold sweet tea, and it just settles at the bottom, and you stir, 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 and for a minute you feel like it's going to dissolve because it's all dispersed, but then a minute later it just settles at the bottom because it's not going in there. So if more solute is added, it will just settle at the bottom. So that's what a saturated solution would look like. And then the last one is supersaturated. So a saturated contains the maximum. A supersaturated solution contains more than the maximum amount of solute at a given temperature. So how is that possible? How do we have more than the maximum? Well, remember, it's at a given temperature. All right, so we're going to play with temperature to make a supersaturated solution. So a supersaturated solution is extremely unstable. Anything that has more than possible is unstable. So if more solute's added, then what actually happens is there's a fast recrystallization of the previously dissolved solute. So if you watch our picture, if we add more, the crystal itself actually gets bigger. So what that means is some of those dissolved particles in the solution will actually attach to the crystal, and the crystal will grow. Now I will show you an example of this in class because it's kind of hard to visualize what supersaturated looks like. So you could Google an example of it. I'm sure there's a YouTube video, plenty of them that show this, but of course I'll show you in class. It's always better to see it in class than to watch a video of it. But you'll be able to see that recrystallization happen. So again, how do we make this? Well, the solubility of a solid solute tends to increase with temperature. So what I do when I make it is I use a sodium acetate, and I will dissolve it in water. And I heat the water up because that will increase the solubility, and I can dissolve a lot more. And then the supersaturated solution is made exactly like that. Heating the solvent, adding the maximum amount of solute at that elevated temperature. Then if you carefully cool it, okay, if any of you have tried to make a supersaturated solution before, sometimes you'll find it's a bust. It just depends. How clean is your flask? Did a piece of dust fall in there? Anything. Did you bump it? I've tried to carry one out in class before, and all I do is shake it a little bit and it'll immediately recrystallize. So it's very unstable. So if you carefully cool it, then you can form a supersaturated solution. But like I said, the second you add another tiny grain of your solute, it's just going to recrystallize out. That's what makes it really cool though. Alright, so let's talk about that recrystallization. So when you take your solvent and you dissolve your solute in there, that is dissolving and makes the solution. Okay, so if we mix a solute and solvent, the solvent will dissolve, you can see I have it color-coded, dissolve the solute, and that makes the solution. However, when we're talking about a supersaturated solution, or we allow some of the solvent to evaporate on a normal solution, then what you'll have is crystallization, and that's when you have the separation. Okay, once you get the separation, you have crystallization happening instead of dissolving. So they're just opposite processes. And of course, as we've talked about in class, if these two opposite processes occur at the same rate, it's called equilibrium. Okay, just keep that in mind. Alright, so we've mainly been talking about solids and liquids, so let's talk about a liquid solution because you can easily mix two liquids together. Sometimes it works, sometimes it doesn't. So two liquids that will dissolve each other are called miscible. So for example, vinegar and water. I can mix those two together, so they're miscible. Two liquids that will not dissolve one another, on the other hand, are called immiscible. So for example, oil and water will separate into layers. Now I know my picture right here has oil and vinegar, but you know, I just pull my pictures off the internet, but then I use my own examples. So we'll just pretend like this just says water. That's fine. So it'll form the layer. I just know that water and oil is a better example because I don't know how many of y'all have mixed vinegar and oil together. But you know, when you mix water and oil together, you get that water layer on bottom and oil on top, and you can stir, 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 and it will appear to mix for a little while, but then that oil layer is just going to float right back up to the top. And like we talked about in a previous chapter, that's because the oil is nonpolar and the water is polar, so they don't want anything to do with each other. So next thing, we've talked a little bit about hydrocarbon molecules before in some various chapters. So hydrocarbons clearly are made of hydrogen and carbon. And so CH bonds are considered nonpolar due to the small difference in electronegativity. So remember, we use that electronegativity chart and subtract. It ends up being like 0.45, I think, when you subtract. And so because the difference is so small, CH bonds overall will act nonpolar. Hydrocarbons tend to be insoluble in polar solvents because, of course, hydrocarbons themselves tend to be nonpolar. And polar solvents will dissolve polar and ionic solutes, but not nonpolar. One way to increase the solubility of a hydrocarbon is to increase the number of polar groups. Because hydrocarbons, sometimes they're long chains of carbons that are just populated with hydrogen atoms. And so if you can put a polar group on there, then that will make the molecule be more polar. And an example is an alcohol group, which is an OH group. Now it's important to keep an OH group and a hydroxide separate. When we talk about OH minus hydroxide, it makes you think of a base, and it makes you think of the OH separating from, you know, the Na plus or something like that. But an alcohol group, this is not a polyatomic ion any longer. Okay, remember, sometimes we talk about how we dabble a little bit in organic, but we don't really go deeply into organic. So this is going a little organic. So this is not a hydroxide. This is an OH group attached to a carbon chain. And you'll see what it looks like. But if you can have an OH group or something similar that can add some polarity, that will help it dissolve. So as the carbon chain of an alcohol increases, the solubility decreases due to the increased London dispersion forces. The molecule starts to act more nonpolar. So here we have one carbon with some hydrogens and an alcohol group, OH. Here we have a long chain of carbons populated with hydrogens and one alcohol group. So about half of this molecule is the polar group, and if you look here, maybe like a tenth of this molecule is a polar group. So this molecule overall is mostly nonpolar, so it's not going to want to dissolve in water. Whereas this one, you know, it's kind of about half and half, so it's more likely to dissolve. So you have to look at not just is there an alcohol group, how much of the molecule is polar versus how much is nonpolar. Because if it's way more nonpolar, like this carbon chain right here, this whole part's nonpolar, we have this tiny little polar part. This is not likely to dissolve, whereas this is. So next thing is network solids. So network solids are not soluble in polar or nonpolar substances due to the strong bonding forces within the solid. So remember, network solids, they are bonded throughout. There's no intermolecular forces. It is a covalent bond throughout. And the two that I want you to remember are diamond, which is of course carbon in the diamond form, and SiO2, silicon dioxide, the main component of sand. Okay, those are the two network solids I want you to know. So we've already discussed they have really high melting and boiling points because they're made of completely of covalent bonds, and so now they don't dissolve well because they are made completely of covalent bonds. You're not just breaking apart ions or intermolecular forces, you're having to sever a covalent bond, and so that clearly takes a lot of energy. So let's look at a sample exercise. So it says, predict whether each of the following substances is more likely to dissolve in the nonpolar solvent carbon tetrachloride or water. Okay, well I already gave you a hint, although you should be able to figure it out on your own, that carbon tetrachloride is nonpolar. Okay, Okay, the way you would figure it out is when you draw it, you would hopefully realize it's tetrahedral and all of the dipoles cancel. I know that's y'all's favorite thing, is having to go back to Vesper theory and draw it. But it ends up being tetrahedral, any dipoles cancel, so it's nonpolar. But see, I was nice and told you nonpolar. Or water. And so hopefully you've just at this point remembered water is polar. Otherwise, what you can do is when you subtract the O and the H, you'll realize it's in the polar range of about 0.5 to 2. And since it's bent, those dipoles do not cancel. So we just discussed in one of the previous slides that hydrocarbons tend to be nonpolar because of that low difference in electronegativity. So nonpolar dissolves nonpolar, so I'm going to put C7H16 under my carbon tetrachloride. Na2SO4. So remember, I've told you in class, if you see a polyatomic ion, it has to be ionic. So polar can dissolve polar or ionic. So since I see a polyatomic ion there, that would dissolve in my polar substance. All right, next is HCl. When you subtract using your electronegativities chart, you're going to get that HCl is polar. Okay, also, if you remember, it's a strong acid, and so it breaks apart as a strong electrolyte. That's another way. Okay, there's lots of different ways to come to the same conclusion in chemistry. All right, and then last one, I2. Obviously, it's two of the same atom bonded together. They're going to share equally, so that would be nonpolar. Or if you wanted to waste time looking up on your electronegativities chart and subtracting the same number from itself, you'll get 0, which is also nonpolar. So I'm going to put my I2 under nonpolar. All right, so just be aware, nonpolar dissolves nonpolar. Polar dissolves polar or ionic. And if you see a polyatomic ion, the rule of thumb is it's ionic. All right, so let's let you try one real quick. All right, so you try this one real quick, so just pause the video, try it, and then I'll obviously explain it right now and you can check your answer. So it says, arrange the following substances in order of increasing solubility in water. Okay, so remember, water's polar, so we're going to go from least polar or most nonpolar to most polar. Okay, so if you look, here we have just a plain hydrocarbon. Here we have a hydrocarbon with one alcohol group. Here we have a hydrocarbon with two alcohol groups. And here we have a hydrocarbon with a Cl attached to it. All right, so first of all, what would be least soluble would be the completely nonpolar hydrocarbon. So what I'm going to do is I'm just going to call this 1, 2, 3, 4. I hope that lined up with what answer I picked to come up on the thing. We'll see what happens. I'll just click past it real quick if it's not the same. All right, so this one is going to be the least polar because there's no polar groups whatsoever. So I'll put my answer up here because I know mine's going to come down here. So 1 is going to be the least polar. All right, next thing we would have to decide is, okay, well, what is more polar, an OH group or a Cl? Well, if you'll remember hydrogen bonding is between H and either N, O, or F because those are the most electronegative. So what would be more polar, the O or the Cl? Well, since the O can take part in hydrogen bonding, the Cl is less polar. Okay, so that's how I would know that this one's next. So 4 would dissolve a little bit more than 1 would. All right, next I'll move on to, of course, my alcohol group because I know OH is more polar than Cl. So 2 would be next. And then how do I know 3 is the most soluble? Because it has 2 alcohol groups. So 3 would be the most soluble. And so that's how you would do that. So hopefully you got it right. Hopefully I just numbered in the same order that I numbered on my own paper. Let's see. Oh, okay, I didn't number them on my own paper. Whew, well, that worked out well. Okay, so I went ahead and put the formulas instead. I wasn't sure if I numbered 1, 2, 3, 4. Oh, well, you know, whatever. All right, so anyway, hopefully you got that right. So let's move on because there is one type of math in this section. And it's very simple, so we'll get to that in just a second. So, as temperature increases, the solubility of a solid solute tends to increase. Now remember, keep in mind, a solid solute tends to increase. A change in pressure does not affect the solubility of a solute. So here is an example of a solubility chart. And so as you can see, most of the lines They're increasing as temperature increases. Now, not all of them, like NaCl is almost a straight line. I mean, well, not a straight line, almost like a zero slope. It does have a tiny slope going. I know it's probably hard to tell there. But there are possible solids that actually get less soluble. There's one right here, but the majority of them get more soluble.
Good morning, Mr. Parr. Your meeting's in the front office. Mr. Parr, your meeting's in the front office.
All right, so moving on. Sorry about that. All right, so now let's talk about a gas. So this is where I keep saying, watch out, I'm talking about a solid. So as the temperature increases, the solubility of a gas tends to decrease. It's the complete opposite of a solid. So if you look, all these gases, they're decreasing as temperature increases. And the gas particles need to be as slow as possible to force them into the liquid. You have to think, why in the world would a gas want to slow down and dissolve into a liquid? But it does happen. You drink carbonated beverages all the time, like Cokes and things like that. They clearly have a gas in there, so how is that happening? Well, one of the things they want to do is decrease the temperature. That's why a cold Coke will have higher carbonation than a Coke that's warm. As pressure increases, the solubility of a gas tends to increase because it's like we're forcing the particles in. Okay, so we have our gas above our liquid. We've dissolved some of it by trying to get it really cold. And then if we put some pressure on there, we can force some more of the particles to dissolve. So that's why when you open a Coke, you always hear the pressure release.
Good morning, Eagles Lake High School. We have a light breakfast for you in the Media Center. Of course, we have a brief faculty meeting. Then, of course, the PM session is for high school during the day. You'll go to your PM session for whatever the county has assigned you have to do. But right now we have light breakfast in the Media Center, and we will see you for a brief faculty meeting. Thank you.
Obviously, I have a faculty meeting in a minute. Sorry about that. Let's move on. All right, so our one math equation that we'll use for this chapter is Henry's law. So Henry's law shows the relationship between pressure and solubility of a gas. So we have S equals Kp. Sometimes you'll see the little sub G, sometimes you won't. It just kind of depends on what you're looking at. So S is the solubility of a gas. Its unit is going to be capital M, which is molarity, or moles per liter. Because molarity is moles per liter. We'll talk more about molarity in section 2. So you can write either unit is fine. The capital M for molarity or moles per liter. K is Henry's law constant. It's different for each solute-solvent pair and changes with temperature. And it has kind of weird units, but it's just so that they can cancel and give us normal units for pressure or our solubility. And so it's moles per liter times atmosphere. And then P is the partial pressure of your gas, and it needs to be in atmospheres because that's what your Henry's law constant is going to be in. So the important thing to remember is if I give you pressure in like kilopascals or torr or millimeters of mercury or something like that, you'll need to convert it to get to ATM so that you can plug it in. All right, so let's look at what one of these looks like. They're really simple. So it says calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 of 4 ATM over the liquid at 25 degrees Celsius. The Henry's law constant for CO2 and water at this temperature is 3.1 times 10 to the negative 2 moles per liter times ATM, or atmospheres. Okay, so the good news is we have ATM, so we don't need to convert. So of course S equals Kp, so then I just plug in. So it tells me my Henry's law constant is 3.1 times 10 to the negative 2 moles per liter times ATM, and then times my pressure of 4 ATM. So if you look, y'all know how I am about units, so our ATM cancel, we're left with moles per liter, which is molarity. Okay, and so when we solve, we get 0.124, and like I said, you can either put, I'm going to put the capital M for molarity, but you can put moles per liter if you would like. Either one is fine. Okay, and so that's how we can calculate. So at that temperature, this is the concentration of CO2 that's in that soft drink. All right, so I'm going to click and let you try the next one. I will tell you on the next one, you're going to need to use the same K value for the next problem. So just pause it for a second, try, and then I'll try it right now. So it says calculate the concentration of CO2 in a soft drink after the bottle's opened and equilibrate it equilibrates at 25 degrees Celsius under a CO2 partial pressure of 3 times 10 to the negative 4 atm. So here we've opened it, and so now our pressure has changed. So let's see if our concentration changes. So we know S is K times P, and so we're going to use the K from the previous problem, because notice we're still at 25 degrees Celsius. We're still talking about the CO2 in the soft drink, so our K does not change. So our K was 3.1 times 10 to the negative 2 moles per liter times ATM. But now our new pressure is 3 times 10 to the negative 4 ATM. And so again, those ATM units, they cancel, and once I solve, I get 9.3 times 10 to the negative 6. And then again, I'm going to put the capital M for molarity, but you're more than welcome to put moles per liter. Okay, so important thing is, like I said, just make sure that your pressure is in the correct units so that the units will cancel. All right, so hopefully you got that right. And let's finish this section up. So what units are usually used to express the solubility of a solute? Well, if you remember from one of the previous slides, we said it's grams of solute per 100 grams of solvent. So grams of solute per 100 grams of solvent. And of course that changes per temperature. Just remember, temperature changes everything. So what would you do to change a saturated solution into an unsaturated solution? Now lots of my students, they always like to say, take some of the solute out. But y'all, if it's dissolved, it's really hard to take it out. The easiest way to change saturated into unsaturated solution would be to add more solvent, because that will reduce the solute per solvent, making it unsaturated. All right, so hopefully you thought the section was as easy as I did, and I'll be making the section 2 video next.